and stays open until next Tuesday evening. So you have plenty of time to get over there to the testing center. A few announcements about that. The sample exams that I've given you, the paper ones, were final exams in a different course years ago. And so you've noticed that in the multiple choice portion of those sample exams, there were questions from kinematics and dynamics and energy and momentum. That's not going to be on your exam. Remember, your exam is just covering the new material on fluids and rotational mechanics. Those two topics will be on the exam. So in that sense, it's more like that online exam that we put out there for you as a practice exam, because that online exam was the exam winter semester. So you can kind of use that to gauge the difficulty of your exam and what to expect there. Yes. The week of Thanksgiving, we will have Tuesday class because Tuesday is an ordinary day. Monday, it turns out, is a Friday instruction day. That doesn't affect us because all of our tutorials are on Thursday and Friday. So by Friday instruction, they mean the following Friday, the Friday after Thanksgiving. So we won't do anything on Monday, but on Tuesday we'll have lecture. And it'll be a fun lecture. We'll be talking about Mach cones and beats and Doppler effect, all the funnest things will be covered on that Tuesday. No one in this class is in a Monday tutorial.
I mean, lecture.
The other section are going to just watch a video of the tutorial instead of going to tutorial because of the holiday. Does everyone have some place to go for Thanksgiving? Talk to your neighbors, see where they're going.
I'm gonna cancel my space.
Okay. Today we're going to start a new topic. The rest of this semester we'll be covering waves, and we're going to start, as we always do, pretty basic. And we're going to cover a lot of ground today, covering the basic concepts involved in waves. And so rest assured that what we cover today, although important, will not be on the midterm that you'll be taking this week. Let's start with a word of prayer. Who would be willing to offer that for us? Nobody? Thank you.
Dear Father in heaven, we thank thee so much for this beautiful morning and for the safety in which we traveled here. We're so grateful for the opportunity to learn physics this morning. We're grateful to be studying something that will help us gain the knowledge to become more like thee. We're so grateful for our religious education and for the blessing of being able to learn with other disciples of Jesus Christ. We're grateful for Dr. Francis and all that he teaches us with so much enthusiasm and excitement. We're so grateful for our Savior Jesus Christ and his atoning sacrifice, the enabling power of his atonement that helps us be able to accomplish more than we would ever be able to do on our own. We pray for the Spirit to be with us today to help us learn, and that would help us in preparation for our tests, that we can study by the Spirit, and that things will be brought to our remembrance. And I pray for anyone here that may be struggling with their mental health, with anxiety or depression, that they will be blessed and supported in their trials. And we say this in the name of Jesus Christ. Amen.
Amen. Thank you so much. Before we get started, I'd like to introduce somebody. Professor Scott Bergeson, would you stand up for us, please, here? Dr. Bergeson is, to a great extent, responsible for me coming to BYU. I was minding my own business up in frozen Montana, and he contacted me and convinced me to come down here. And I'm very grateful that he did. Thank you. Thank you. He wasn't the only one that convinced me. My wife and I went to the temple and were told in no uncertain terms that we had to move. And so, and I've told you this before, I thought for months that I was doing the Lord a favor. I thought, oh man, that was a hard move. I really did the Lord a solid. But I have come to realize over this last year that he was blessing me. He was doing me a favor, because you people have just made my whole life so much happier. I just love walking across campus and seeing your faces and the smiles and the radiance that comes from you. I tell you, I wasn't getting that in Montana, but it's good to be here. Okay, some of us are feeling really comfortable when we get the right answer to the homework, even if we get that right answer with help from the TAs. But then when we get to the exam and we're all by our onesies, it doesn't go as well. So I would encourage you to go back and look at those homework problems with the key now. Now that you've already done the homework and gotten the right answer, look at the key and make sure that you understand each step of the reasoning that goes into those answers. Also, when you take those practice exams, don't look at the key, okay? Don't just follow down the key and say, oh, I see what Greg did there. Yeah, that's pretty clever. That's not going to get you ready. You have to pretend it's the real thing. And then after you've taken that exam, go back and grade yourself. And if you find that you're just not seeing how I got the answers in that key, please come see me. Come talk to me, and we can talk about it and make sure that you understand how to solve those problems, because it's better not to learn those things during the exam. Tonight, we're having a review session in this room. It was going to start at 7, but then we found that a lot of you were still struggling with the idea of buoyancy. So we pushed it up to 6:30. I'll still go to 8, but the first half hour, I'm just going to concentrate on buoyancy and make sure that everyone knows how to find that buoyant force really, really quickly. Okay, questions about the exam or the review session? The review session will be recorded. That was your question? I read your mind. Yes.
Oh, if you get on the homework, don't change some details. Is there a way that without getting it wrong, going back to the homework, we can change the details and move over again?
Let me see if I heard you correctly. Can you go back to the homework after you've already submitted it and get the same numbers or different numbers? Different numbers? I know that I can when I go in and pretend to be a student. Scott, it's not, I'm sorry, it's not in the software. Okay, but I could just give you my password and then you could change everyone's grade. And yes. Okay. Folks, last day, we ran out of time before we solved this problem. Let me just remind you, we have a meter stick, and this meter stick is in equilibrium, okay? Now, what that means, we know, is that there's no acceleration. And in the olden days, that meant the linear acceleration of the center of mass. But now we know that things can rotate. And so when we say equilibrium, we mean not only the linear acceleration is zero, but also the angular acceleration is zero. It's not speeding up in an angular way. And indeed, it's not even moving. And we find we can do that with 3 strings. If we pull to the right with 6 newtons and we pull on this end down with 2 newtons, and if we pull with a 3rd string, we can keep that meter stick from moving at all. But we need to pull just right with that 3rd string. And what we want here is how hard should I pull, what angle should I pull, and where should I pull? Okay, 3 things I'm looking for. How hard should I pull? What angle should I pull? And where should I pull relative to the left end? Now, we're going to work this problem. Let me back up. Last day I asked you if you could find that buoyant force. And a lot of you very quickly found 3 newtons. How? But some of you didn't. Okay? Now, remember, the buoyant force is just the weight of the, in this case, water displaced. And we're told in this problem that the volume of that meter stick is 300 centimeters cubed. Now, we've known how to find the weight of something for a long time. Okay, we just take the number of kilograms, multiply it by 9.8, let's call it 10. Okay, pretend we're on that planet far away. And then we get the weight. But the problem is, I got the volume of that meter stick, not the number of kilograms of that meter stick. But that's why water is so easy to work with, because the density of water is 1. 1 what? 1 gram for each centimeter cubed. So if I got 300 centimeters cubed, and there's 1 gram for each, I got 300 grams. Now you know, and you've known for a long time, that before I multiply by that 9.8, let's call it 10, I've got to convert it to kilograms. And 300 grams is 0.3 kilograms. When I multiply that by 10, I get my 3 newtons. Now, if that was a mystery, if that just went right over your head, come tonight at 6:30 and let's talk about that in detail, okay? Because on the test, that might not be water. That might be heavy cream. That might be ethyl alcohol, something with a different density than 1. And we'll work those kind of problems tonight. Okay, so let's get rid of the screen here a little bit. And get a little light on the subject. Oh, this is going to be awkward, isn't it? I'm sorry. Okay. So, with equilibrium, we have linear acceleration equals 0 and angular acceleration equals 0. This tells me that the net force, which causes the mass to accelerate, if this is 0, then so is this. Okay? Now from here, what I know is that all the force left must equal all the force right. And I know that all the force up has to equal all the force down. Now from here, we have the rotational version of Newton's second law. The net torque causes a moment of inertia to angularly accelerate. If this is 0, that means that all the torque clockwise has to balance all the torque counterclockwise. Now, remember what we're looking for. We are looking for the magnitude of T3. We're looking for the theta, and we're looking for R. Well, I'm gonna change that a little bit, make it easier. If I break up T3 into its X part and its Y part, then what I'm looking for is TX 3X and T3Y and R. Now, if I know these two, I can find the magnitude of T. We've done that with Pythagorean theorem over and over again. I can use the inverse tangent to find this angle, and these are going to be easier to find. Okay, let's start with T3X. All the force left has to balance all, oh, wait. What do we need to do here? Once we break up that T3 into its components, we throw away the original and we use the components, right? We remember that? Okay, so all the force left has to balance all the force right. I've only got one force left, one force right, so this has to be 6 newtons. Okay, and I'm going to write it as, it's got to be equal to T2, which is 6 newtons. Now, all the force up has to equal all the force down. Well, I've got 6 newtons down, 2 and 4. I got to have 6 newtons up. The buoyant force was 3 of that. And so that means T3Y has to be 3 newtons. Okay, so from here I can say that the magnitude of T3 is going to be the square root of 6 newtons squared plus 3 newtons squared, whatever that is. And I know that we were asked to find the angle relative to the vertical, and you can see that that's going to be the inverse tangent of the opposite side, which would be the 6 newtons over the 3 newtons, the adjacent side, and that's going to be 63.4 degrees. Well, what about R? Well, we've used these two equations, so let's use the torque equation. And the question is, about what pivot point should I balance those torques? Again, this meter stick isn't rotating about any point. I can choose any point to balance the torques about and get the right answer. But some points are easier than others. You'll notice that if I choose that pivot point right there, I don't have to worry about the torque due to T3X because there's no lever arm. I don't have to worry about the torque due to T1 because there's no lever arm. I don't have to worry about the torque due to T2 because there's no lever arm. The only forces that give me a torque about that pivot point are T3Y, the buoyant force, and the weight. Okay? And so I just have to figure out which of those are clockwise torques and which of those are counterclockwise torques. And you remember how we do that. We pretend that we've driven a golden spike right through that pivot point, forcing it to be a hinge, forcing this meter stick to revolve around that hinge. And then we ask, if this were the only force acting on the meter stick, would it try to make that meter stick rotate about the hinge clockwise or counterclockwise? Well, that's going to be counterclockwise. That's going to be counterclockwise. That's going to be clockwise. And so what I've got is T3Y, which we said was 3 newtons, times its distance to the pivot, which is R. And then we have the buoyant force. Whoa, wait a minute, Greg. No. The clockwise one is the weight. I'm sorry. 4 newtons. But how far is it from the pivot? How do we know it's not given in the problem? But it's a meter stick, right? So that's got to be half a meter. Okay. Yeah. Meter sticks are that long. Okay. In the counterclockwise, we've got the 3 newtons, buoyant force, also times 0.5 meters. And then we have 3 newtons times R. Now, folks, the reason we separate the clockwise from the counterclockwise torques is because we have so many minus signs in this introductory physics class. The minus sign is one of our most confusing concepts because we use it for all different things. Sometimes we use it for direction. Sometimes we use it to see whether our bank account's filling or emptying. We don't need another minus sign. If you separate out the clockwise from the counterclockwise torques, one on one side of the equal sign, one on the other, you will never, ever have a minus sign in this equation, okay? So when I solve for R here, what I get is 1/6 of a meter. A problem that looked very, very challenging turns out to be very, very simple. Talk to your neighbor. See if your neighbor followed that problem.
Most of the problems where you.
Oh, I did one of those on the practice yesterday.
Yes. Yeah. From the left end.
This was like, I just danced, I didn't make it 150. I haven't seen it.
I thought when it didn't ask you to like find a value, just ask you what would happen. Make sure you get to the less.
It's not over that.
Okay. Questions before we go on to a new topic? Yes, sir.
Can you explain the minus sign thing?
The what?
Can you explain the minus sign thing? Like never use a minus sign when you're doing.
Oh, yes. When we were doing Newton's second law and we were having force 1 up and a weight down and force 2 down. When we did F net equals MA, we defined a coordinate system. And we added these forces, but we added them as vectors. So this would be F1 and it would be up, so it'd be positive. And then we would subtract F2. What we're really doing is adding it, but in the negative direction. And then also the weight, and then that would equal MA. With torque, we know that if I can draw the picture on a flat piece of paper or a screen, the torque's either out of the page or into the page. And rather than figure out which of those is plus and which is minus, I do the trick that I do here. If acceleration is 0, I can also just bring all of these negatives to the other side and say force up equals force down. And when I do it that way, there are no minus signs. I got rid of them. Well, likewise with this torque equation, I'm letting one of those directions, maybe out of the page, be positive and the other one be negative, but I don't want to keep track of that. So if I just look at them fighting each other, one trying to make it go clockwise, one trying to make it go counterclockwise, I don't have to do minus signs. Thank you for asking that question. Other questions? Question for Sam. Okay. Yes, sir.
There's been some problems where it asks about moving like the tension force to the right or to the left of the pivot. How do you set those up? Where it's like if you move the tension to the right, does it increase or decrease?
You essentially start the problem again with that new R and see whether it's balanced still. In all the problems we've had in the sample exams and the homework, it remained balanced by something else getting smaller. And so essentially you just go back to the start with that cable in the new location and then figure out what that does to the other cables. Okay. Okay. Oh, all the way on the back, old man coming.
I had a question on the angle point, because if I would have done this problem myself, I would have switched them around. So how did you come to the point of having over 3 instead of 3?
Well, I'm glad you asked that. I've drawn the components like this and like that, where this was T3Y and T3X. But I could have moved this up here like that, where this was T3, and we're looking for this angle here. Okay. And I only drew that T3 down here to make it clear that I can think of those components as strings that are pulling right at this point here where the string is attached. And if I draw this component down here, it's very clear that there's no lever arm, that it's going right through the pivot point. Now, remember the tangent of theta is defined as the opposite over the adjacent. And this would be the opposite the angle. And so 6 is going on top. Does that answer your question? Okay. Now, we could have looked for this angle here, but let's give it a different Greek symbol. But the textbook didn't ask for that angle. In that case, we would have done 3/6. Okay. Folks, we are going to do just a really quick review before we start our new topic. I have here, for your enjoyment, a spring. And I find that if I hang 500 grams or half a kilogram on there, what I find is that it stretches the spring to a new equilibrium position. And we call that equilibrium stretch, we've been here before, delta S. And if I put half a kilogram on there, I measure that that stretches it by 29 centimeters or 0.29 meters. So with your neighbor, find me the spring constant of that spring. What is the spring constant of that spring?
MGH just be. I know it's 1/2. Which is. By 2, so then divide by.
Won't put that in your.
You wanted it same. I guess if you said you could just.
Are any of you sitting next to someone that doesn't remember? Yeah, don't raise your hand. He was quick to give you up. Okay. What equation do we use, folks? Shout it out. Hook, 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 Hooke's law. Hooke's law. Remember after Robert Hooke, the nemesis of Sir Isaac Newton? And remember that minus sign, again, we have so many minus signs, and this one just doesn't tell us that much. It tells us if I stretch a spring in this direction, it pulls in the opposite direction. And so often we just ignore this minus sign and worry about the magnitude. Now, if I use that formula, first of all, I need a force. And anytime I need a force, I draw a free body diagram. Since I'm doing an actual experiment here, I'm going to use 9.8 instead of 10. I'm not going to pretend that we're on that planet far away. And so with gravitational field strength 9.8, the weight of that half kilogram is going to be half of 9.8 or 4.9 newtons. I know that there's no acceleration as it just sits there, so that that force by the spring must also be 4.9 newtons. And the stretch, which I put in meters, is my delta S. When I solve that, I get a number that no one in the room cares about, 16.9 newtons for each meter. Now, you remember what K means. It's the stiffness of the spring. If this spring came off a Chevy Cavalier, it'd have a huge value for K. And we found that the energy stored in a spring that's compressed or stretched depends on that K. And any of you that have worked on a compressed suspension spring on a car know that it's pretty scary. The capacity to do damage is great. Now, that's not what we're about today. That's not what we came here to talk about. That's what we're talking about. Okay, that's the new topic. And we call this simple harmonic motion. And I hope today to convince you that the simple is really simple, that there is a simple in simple harmonic motion. Now, before we go any further, I'd like to see by show of hands, how many of you have always wanted to understand this problem of a mass bouncing up and down on a spring? Liars. You notice my hand's not up. A mass bobbing up and down on a spring. Big deal. But it is a big deal. It's a very big deal. Because if we could see with very special glasses that could look microscopically at anything solid, what we would see was a lattice work of molecules that act like masses, and the interaction between those molecules act like springs. If we can understand this, we go a long way to understanding this, the world around us, the world around us. Now, I did not always fully appreciate that. Indeed, when I first arrived at MIT as a graduate student, I was terrified. I was terrified, and I knew that I didn't belong there. I knew that they had made a mistake. And one of the first things that they do to the graduate students is give them a 5-hour exam called the qualifying exam to see whether you were really qualified to be there. And if you failed that exam, you had to get back on the bus and go home. Now, they gave that exam because they were bringing geeks from all over the world. And they didn't know how to gauge the grades in this country with the grades in that country. So they had this exam to weed out people like me. Well, the first question on the exam was a big, heavy motor sitting on a thick rubber mat. And they wanted to know what angular velocity, what omega, you should make this motor go to get the biggest bounce on the rubber mat. Now, I got my degree from BYU. I did okay. And I have never seen anything remotely like that. I felt like BYU had failed me, that they had not prepared me for graduate school. And I was getting ready to get back on that bus. I was trying to figure out how to call my wife and tell her that time to go home. And then I noticed that that motor was just a mass. And that rubber mat was acting like a spring. And suddenly I saw that that complicated problem that I had never seen before was a simple problem that I had seen over and over again. And I quickly solved that problem. I turned the page, and it was another problem that was dressed up as something complicated, but was that. I giggled, and I got to stay at MIT. And because of that, I get to be here working with you. So this may not be important to you, but it's very important to me. It's changed my life. Okay. Oh, yeah, I love that. I love that. Okay, let's talk about this simple harmonic motion, SHM. We can characterize it by the timing, and we can describe the timing two different ways. We can talk about the period of the bounce. Now, the period is the time it takes to make one complete oscillation, to go from top down to bottom and back up to top, to get back to the starting place with the same starting conditions, okay? Now, we can also talk about the frequency, the number of oscillations that happen in a unit of time, and the unit we take is usually a second, okay? Now, we can also talk about the amplitude of the oscillation. Now, the amplitude is the furthest it gets from equilibrium. And remember, equilibrium is its happy place, where it would stay forever if it were not perturbed, okay? And so the amplitude is the furthest it gets away from that happy spot. Now, again, these are pretty basic ideas that you encountered in your reading for today. So just quickly think about this. A block on a spring bounces up and down every 0.25 seconds. How many times does it bounce up and down in 1 second? Shout it out. 4. That's not hard. That's not hard. And now you have one of the basic fundamental ideas, and that is if the period is 1/4 of a second, the frequency is 4 times per second. We call that 4 hertz to honor a dead physics professor. Not a bad thing to do with your life. Think about maybe making a contribution in Dr. Bergeson's name after he dies.
Actually, -1 is my constant.
You know I can't hear you, right?
Gosh, look at him.
Oh, he wants the minus sign. Okay, the minus sign will from now on be called the Bergeson. Okay. What we see is that if you know one, you know the other, because the frequency is just 1 over the period, and the period is just 1 over the frequency. Okay, so you can also think of that hertz as a inverse second or per second. Okay. Old exam question. Get out your clickers, please. I'm going to go this way so that I don't disturb the baby. Okay, let me get you started here. Okay, now you can click. This is a crying shame. This was an old exam question, which means it's not going to be in your exam, but it sure would be nice to have this one on your exam because it's an easy one.
What is she talking about?
Oh.
Yeah, I think that's wrong. Equilibrium.
Play that Jesse's house.
Suddenly occurs to me that some of you have never had anything but a digital watch. Second hand goes once around each minute. Okay, last call. Get your attendance points. Good. Okay, the correct answer is D. The frequency is just the number of cycles divided by the number of seconds it takes, or in 1 second. Remember, when you have a definition that is a ratio, something divided by something else, make the basement 1 to get a gut feeling understanding of it. Well, in this case, we're going to go the opposite way and say it goes 1 cycle in 60 seconds, and that gives me 1 over 60 of a hertz. Okay. So we would circle D. Okay, suppose I keep this spring, but I want to change the mass. I started with 1/2 kilogram. I have a whole collection of masses here. What kind of mass would I want if I wanted to increase the period? Now, really quick, ask yourself, what's that going to do? Is that going to make it bounce faster or slower? Which is it? Yeah, the period is how much time it takes to make one oscillation. So it's going to go slower. So should I grab a bigger mass or a smaller mass? Shout it out. Yeah, bigger, because you know it's harder to speed up and slow down something that's bigger. Indeed, that was my post isn't even high enough. Who saw that coming? Okay. We can fix that. Wall, 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 wall. Okay, and you remember that with this one we had wall, 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 wall. Okay, so we slowed it down. Now, what if we wanted to increase the frequency? Well, it makes sense that if a bigger mass is going to slow things down, a smaller mass is going to speed things up. Boing, 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 boing. And if I go even smaller, it's going to fly right off. Boing. I called it. Okay, let's see if we can get this thing to go. Yeah, there we go. There we go. Okay. Now, new question. I have this block that's attached to this spring, and it's oscillating back and forth on this frictionless table. Now, folks, in this class, we will always have this block sliding back and forth on a frictionless table. We can solve the problem with friction, but it involves a little bit of messy math, a differential equation. We handle that problem in, I believe it's the 321 class here at BYU, and it's a class that none of us who are going to be doctors are going to have to take. Okay, so in this class, we're always just going to assume that that level surface is frictionless so that we don't have to worry about that mathematics. Now, in this case, the block is turning around at these two locations at 1.25 meters from the left wall and 1.75 meters from the left wall. And the question is, what is the amplitude of this motion? And we're going to again use our clickers.
From the.
This is the difference. We're gonna have to go.
That's my thinking.
I like that thought process. Thank you.
That's.
If it's compressed. If it's only.
Oh,
You sure are?
Oh, and it was.
Loady load.
Like average, yes, one. I don't know.
Okay, last call, get your attendance points. There we go. I think that's how many we had last time. Whoa, we don't know. We don't know. And I was going to take you all to Disney World if you all got that right. Oh, that's too bad. Okay, let's talk about it. Nope. Oh. Disney World, here we come. No. Okay. So, let's remember what amplitude is. Amplitude is the furthest it gets away from where? Equilibrium. So the first thing we have to do is figure out where equilibrium is. Well, for a spring that's horizontal, equilibrium is the length of the spring that it was when it came out of the box from the factory. When you opened the box and took it out, how long was it? And that's going to be halfway between the two turnaround points. When it's over here, the spring is compressed. When the block's over here, the spring is scrunched up. When the block's over here, the spring is stretched out. And so the equilibrium position would be halfway between. And the distance from the turnaround points to that equilibrium point is 1/4 of a meter. Check with your neighbor, see if your neighbor followed that.
That's where like.
Okay. That's a very basic idea, but it's an idea that I find can really mess up your work in the homework and on exams. If you are thinking of something different, when I say the word amplitude, you get different answers. Okay, so make sure that you understand how we define amplitude. Okay. Suppose we have this mass on a spring, and let's suppose that it had a frequency of 3 times each second. So it's a different mass on a different spring. We would like to figure out as many different ways as possible to increase this rate. So with your neighbor, figure out as many different ways that you could increase this rate of oscillation. Talk to your neighbor. It should be noisy in here.
Faster? Yeah.
Make it slow.
Or you went like this?
There'll be more. No, just 5 foot in it.
It's got to start with momentum, like if you have to like spin it.
Push up on that. One first.
I think.
Oscillations are like.
Right.
Right.
Push it.
I bet you there's another.
Oh, no.
If you pull it down.
Then there's pull it down hard.
It's like a reaction. Gravity.
Back.
Here's the answer. That's right.
Okay, let's share. Brave soul, raise your hand. What did you come up with? Where are you, brave soul?
Increase the mass.
Increase the mass. We want to make the frequency increase. Decrease the mass, okay? So we're going to decrease the mass. Good. What else? Brave soul, other brave soul. Make the spring stiffer. Okay, good. Other brave soul. Don't pull down as far, okay? Don't pull down as far. What else? Nothing else? Oh, I have good news for you people. I have good news for you people. That's it. That's it. Let me explore this. Don't pull down as far. Okay. I'm going to pull down far. 1, 2, 3, 4, 5, 6. Now I'm going to pull down not as far. 1, 2, 3, 4, 5, 6. Now I'm going to pull down really far. 1, 2, 3, 4, 5, 6. Monotonous, isn't it? That's the simple in simple harmonic motion. That's what makes this so easy. It only depends on the mass and the stiffness of the spring. M and K is all that matters. Now we have other things like, what if I were to get it started really quick by hitting it? 1, 2, 3, 4, 5. Doesn't matter. It doesn't matter. Okay. Now it turns out that's our most important point. The period, or indeed the frequency of an oscillator, is only related to those two things. The stiffness of the spring, that would be the restoring force, and how hard it is to get the system moving, that would be the mass, the inertia. It does not tell you anything about how the system got started, and it's independent of the amplitude. Independent of the amplitude. Now you'll see when you start working those homework problems that in some of these problems, I'll give you the amplitude. I'll give you the color of the block if you want, you know, the time of day. But you're going to be doctors. And one of the things you need to do as doctors is figure out what's important, okay, and what's not important. Okay, okay. So it's independent of the amplitude. So you're going to ignore that in problems dealing with simple harmonic motion. Now, in a perfect world, I would derive the equation relating the frequency and or the period to those two factors. But that involves, again, some mathematics we're not ready for, a differential equation that's built on our understanding of calculus. And on the very first day of class, we entered into a pact that we would not use calculus in this class. Okay, you all agreed to that. Okay, and so what I'm doing is just asking you to trust me. And I think that Dr. Bergensen will back me up on this. If we did the math, the period is going to be equal to 2 pi times the square root of the mass divided by K. And that formula will be on the front page of your final exam. Now, because the frequency is just 1 over the period, I also have a formula for the frequency. I just turned the other formula upside down. Upside down. Okay, so that's a formula that you should have in your notes and be ready to use. And I hope you see that it gives me another way of finding the spring constant of this spring. Okay, what I can do, if I take this ½ kilogram and I put it back on this spring, if I just measure how many seconds it takes to make one up and down. Now again, this is a ½ kilogram, and I'm going to measure how many times it takes to go up and down 10 times. So I'm going to, oh, first of all, that's not a ½ kilogram. Someone should have spoken to me about that. Just let the old man go and do the wrong thing. Pretend that he just, you're going to find me grazing at the Albertsons salad bar someday. Okay. Okay, so that was 11 seconds. And the amplitude of the oscillation is, do we care? We do not care. Let's leave that blank. Now, if I go to that equation and I want to solve for K, you can see that there's some problems. First of all, K is underneath that square root sign, And also it's in the basement. And so if I want to get rid of that square root sign, I have to square both sides. And so I get t squared on the left and 4 pi squared m over k on the right. Now, in order to get a formula for k, I cross multiply and I get that formula there. Now, here's a little trick that'll speed up your calculations. It turns out that pi squared is really, really close to 10, even closer than the 9.8 that we usually call 10, okay? So in this case, we can just make pi squared 10, m is a half, 4 times a half is 2, so that's 20 on top divided by 1.1 squared, and what we get is very close. We get 16.3, which is very close to the 16.9 that we got before. And the reason that it's not exactly the same is because I didn't do anywhere near an accurate job of timing the oscillation. Okay, check that your neighbor is grateful for that second way to find K. Okay, again, I've given you 2 ways to calculate something that many of you didn't care about. The first way we call the static method, where I just hang a mass on a spring and use Hooke's law. We did that at the beginning of our discussion. The second approach we call the dynamic method, and in that case, we have to make it dynamic. We have to bounce it, and we have to measure the period. And then if we know the mass, we can calculate the spring constant using this formula here. Okay? Now in your homework, sometimes you're given enough information to use the static method. Sometimes you're given enough information to use the dynamic method. Here's a problem. I've got a 2 kilogram block hanging from a spring, and it oscillates with a period of 1 second. What mass of block hung from the same spring would have twice the period, a period of 2 seconds? Talk to your neighbor. What would it be? What mass?
Okay, so 2 kilogram block takes for the spring.
Doubling T. Right, but.
Okay, let's talk about it. I want the left side of this equation to double. Okay? And that means the right side of that equation has to double. But the only thing I can change is the mass. But because that mass is underneath the square root sign, I can't just double the mass. I'm going to have to quadruple the mass. And so instead of 2 kilograms, I would want 8 kilograms. 4 times as much mass would double the period. See if your neighbor followed that, please. Yes, sir.
You have to double 2 pi also.
No. The 2 pi would stay the same. If I just take one, since they're multiplied together, say 3 times 4 is 12. If I just double the 4, I'm going to double the product. Okay. Okay. Now, a lot of the problems in your homework, and indeed, I'll promise you right now, at least 2 of the problems on your final exam will deal with blocks that are going back and forth on a frictionless surface, always horizontal, And these would be the turning points. And you're going to be asked some questions about that block on that spring. Now, the amplitude is the distance from the equilibrium point. This is the point where if I just put that block there and set it there not moving, it'd still be there tomorrow, okay? But if I pull that block, stretching the spring, it'll go bouncing back and forth from here to there, to there, to there, to there, okay? Now, where's the net force zero on that block? Yeah, right there, okay? At equilibrium. That's what equilibrium means. It either means net force equals zero or acceleration zero, but that's the same by Newton's second law. Now, at that point, the spring is neither stretched nor compressed, so it's neither pushing nor pulling. Now, if I look over there at the turnaround point on the left and I draw a free body diagram, I've got the weight down, I've got the table pushing up, but we know that those cancel each other out because there's no acceleration up or down for this block. The only other force acting on that block is the spring, and it's pushing to the right. Now, if I look at the net force, in other words, I add up all those forces, that's this right here. And I say that it's Ka. Now, wait a minute, Greg. You said before that Hooke's law was the force by a spring is K times delta S. Well, which is it, Greg? Is it K times delta S or is it K times capital A? Which is it? Yes. Okay. Hooke's law always applied. The force by a spring is always K delta S. But what is delta S when it's at the turnaround point? A, capital A. So this is just one particular value of Hooke's law when delta S is equal to the amplitude, capital A. Okay? Now, if I look over here, I get the same free body diagram, but now the force by the spring is to the left, and I get a net force of Ka that way. Now, if I were to ask you, where's the acceleration of that block zero? Where would it be? Tell your neighbor real quick. Where would it be?
Well, the ends isn't it?
Okay.
The acceleration would be that.
Is the acceleration zero at the turnaround points? No or heck no? Heck no. That's where the acceleration is the biggest. Where the net force is the biggest is at the turnaround point. The net force is zero at the equilibrium, and that's where the acceleration is zero. Okay? So A is at its max, where the velocity is zero. And A is zero, where the velocity is the maximum. They're opposite of each other. That makes sense? Are there questions on that? The acceleration is biggest at the turnaround points, but you got to stop to turn around. So the velocity is zero at the turnaround points. But at equilibrium, the velocity is the biggest it's ever going to be. It was speeding up as it came to equilibrium. It's going to be slowing down when it goes past. It's going fastest as it races through that equilibrium point. And that's where it has zero acceleration. Okay, but just at that point, it was speeding up. It will be slowing down. Remember, that's a transition point where you're pulling your foot off the gas and reaching for the brake. Okay, the acceleration is zero there. Now, we also have another version of the mass on a spring that we started with, and that's the vertical spring, where we put the mass on that spring and we stretch it out to a new equilibrium point. a new happy place, okay? And then if we pull it away from its happy place, some distance capital A, it's going to bounce boing, 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 above that new equilibrium and below that new equilibrium. Now, where does the net force equal 0? Well, right here at the equilibrium point. If I just left it there without any motion, it would still be there tomorrow. This is different because now the spring is stretched at equilibrium. It's not the length it was when it came out of the box from the factory. Because now that stretch of the spring has to balance the weight. There's no table to do that. Now, if I draw a free body diagram, I've got the weight down and I've got the force by the spring up. Now, if I look at this point up here, the weight is still the same, but now the spring is not as stretched. It is stretched a little bit, but not as much as it was down here. And so this diagram doesn't scream balance anymore. It screams down. And we can show that, and this is a little bit messy, but we can show that the magnitude of that net force is again K times A. K times A. If I look down here at this turnaround point, the weight is the same. You can only change that through diet or exercise. But now the stretch of the spring is large, and my diagram screams up again by K capital A. Now, because this is a little bit messier than the horizontal problem, on your final exam, the problems will deal, where you need to do calculations, the problem will deal with the horizontal spring problem. But I hope you see that we're just using Newton's second law, the one law to rule them all and in the darkness find them. Okay, quick question. Question? Nope. Off. We have this spring, it has an unstretched length, and we put a block on it, and it stretches down to here, and then we pull it down a distance A, and it's bouncing up and down, and we're using this as a clock. It has a period of oscillation of 1.2 seconds. If we were to take this clock to the moon, what's going to change? What's going to change and what's not going to change? First of all, what about the unstretched length of the spring? Will that be different on the moon than it is on Earth? Remember, on the moon, we have a weaker gravitational field strength, 1/6 as much. The answer to that question I just asked you, does the unstretched length change, is it depends, okay? Often we ignore the mass of the spring relative to the mass of the block, because in many situations, the mass of the spring is very much smaller than the mass of the block that's bouncing on it. And in that case, taking it to the moon is not going to make any difference. But if we don't ignore that weight of the spring, it's going to be stretched a little bit due to its own weight on Earth and not as much on the moon. And so again, that depends on what assumptions we are making. So the unstretched length would stay the same. What about this distance D to the new equilibrium? Would that change? Yes or no? Shout it out. Shout it again. Yes. Okay. Because the moon is not pulling as hard on the block, it won't stretch the spring as much to get to that new happy place, so that's different. What about A, capital A? Is that going to be the same or different, people? Shout it out. Shout it out. I can make it whatever I want. It just depends how much I pull it down. I can make it 5 centimeters, 10 centimeters, 15 centimeters, whatever I want. And so that was a trick question. I can make A the same, it doesn't matter. Now, what about the period? Well, the period only depends on two things. It only depends on the mass, and we know mass doesn't change when you take it to the moon. Mass is how hard it is to shake something. And it's just as hard on the moon as it is here on Earth. The K value, the stiffness of the spring, that was determined when they made the spring at the factory. That's fixed. Taking it to the moon's not going to change that. So if you took this thing to the moon and bounced that mass on that spring, it would still have the period 1.2 seconds. Now, we're going to, in the interest of time, skip ahead here real quick. In your homework, you have problems where yes,
Sorry, real quick, could you explain one more time why the unstretched length stays the same?
I'm sorry.
Explain one more time why the unstretched length stays the same.
Oh, if it's not sagging under its own weight because it doesn't have any weight, then it doesn't matter where it's not sagging. Okay, we learned when we were talking about energy that if we include in our system both the spring and the block, that the total energy of the system stays the same as it goes back and forth. The energy sloshes back and forth between the kinetic energy of the block and the potential energy of the spring. But the total energy stays the same, and that's what allows us to solve a bunch of problems. Because at the turnaround points, all of the energy is in the spring. At equilibrium, all of the energy is in the motion of the block, and then it's in the spring again at the other turnaround point. But whatever I have there is equal to whatever I have there is equal to whatever I have there. Now, before you go, so that I don't have to bring these demos back again and schlep them all the way from the physics building, we have two different kinds of, I'll bring them next time. You guys go to the forum, okay? Go find out why families are important.
Got me right here.